Thank you, everyone, for telling us in the chat where you're from. And so I'm Pearl Winchester. I'm originally from New Caledonia, and right now I'm in France. I'm a tropical island water specialist, IT engineer at the basis with GIS, and also a public policy coordinator. And so you can have access to my LinkedIn profile. Nicolas is co-animating today, but right now he's in the car, so I'm not going to give him the voice because there's a lot of background noise. But Nicolas is working at the SPC in Fiji, and is currently completing his PhD around hydrology and citizen science. So it's the same. We can share his LinkedIn in the chat if you want. And we also have Dr. Chris Leong from Fiji that is working in Japan now at the Research Institute for Humanity and Nature, and he's an hydrogeologist. So as I said, if you can please introduce yourself in the chat so our speakers know who you are and where you are from. And I'm going to let Niels and Jackie introduce themselves very quickly, please. So Niels.
Yeah, thank you. Thanks a lot for the invitation. I'm Niels Mostorff. I'm from Bremen in Germany, and I'm working at the Leibniz Center for Tropical Marine Research. In that capacity, I've just recently been to Fiji in January, which was a really nice visit. And I'm a coastal hydrogeologist working on groundwater resources, but also the effects of groundwater in coastal ecosystems, both at the local scale and at the global scale. I'm using GIS a lot and a little bit of modeling. And I'm really pleased to be talking soon.
Thank you, Niels. Jackie?
Thanks, Pearl, and thanks, everyone. Hi, I'm Jackie Reed. I'm a senior hydrologist at SPC, the Pacific Community, based in Suva, Fiji. I've been working here, working closely with our country counterparts on supporting improved hydrological services, particularly with a focus on improving flood early warning. So pleased to be here and looking forward to the discussion. Thank you.
Great. So yes, if you have any questions for the audience, don't feel free to type it in the chat while the speakers are talking, so we can actually get the interaction at the end of the talks. So what's up for today? I'm gonna start introducing what is the IAHS Pacific Islands Country Territories Working Group. Then it's gonna be Niels that will be doing this first talk. There will be a small question time here and interaction, and then Jackie, and then we will have another time for questions and answer. Quick bibliographic review if we still have some time, and then what is next, so the schedule for 2026 for the working group and the webinars we organize. And so just a reminder, we used to be the community of Oceania Geospatial Water Resource Work Group. And I don't know if you remember, but last year we were accepted by the International Association of Hydrological Sciences to create a Pacific Island countries territories working group. So we are now the IAHS PICTs working group, to be short. And so just so you know what is the IAHS, it's international association that is part of a bigger union on around geodesy and geophysics. And so if you want more information, you can go on their website to understand what is the role of the EUGG and the International Association of Hydrological Sciences. For us, for the working group, our main focus is to share information and knowledge for the benefits of the Pacific Islands and Oceania around geospatial, GIS, satellite, but also for the water resources. And so we have a LinkedIn group, but you can join. Everybody is welcome. And so for the topics, it's very wide. We are dealing with everything around the great water cycle, but not too much around ocean, because we know that it's another big story. So we are more focusing on freshwater, groundwater, climate, etc., around water, the water resources. Our idea is really to have some sharing, collaboration in the community around sustainable development. And as we are many Pacific islands, we really want to create some bridges between the islands around geospatial and water resources in general. And so the working group now, as we are part of the official association, we have some board members, and so you have the names here. Sorry, there's a small bug here. Visheshni is here. This is Vani, and this is Arti. So we are from different countries because Chris is in Japan. I'm currently in France. Nick is in Fiji. Vani is in Samoa, and Visheshni is also in Fiji. And so the good thing with the creation of this working group is that we are now eligible for some international grants, and we have some support if we organize some capacity development workshop and things like this. So if you want to join the board, everybody is free. You can just scan here and fill up the form, and you can be part of the team. If you have any questions, just type them in the chat and we can talk about it, no problem. And so I'm just going to give the floor to Niels now. Up and stop sharing my screen.
Thanks a lot. I'll be trying to share my screen and just try it before I share the entire screen so that it's there I can even share the slideshow. So I'll try that one. Can you see my screen?
I think it's coming up. Yes, it's working. That's the good one. Go ahead.
Perfect. Yeah, so welcome also from my side, everyone. It's a pleasure to be here or to talk to you. And I have seen a lot of different professions also in the chat just before. I fear for the hydrogeologists, some things may feel like a repetition, but I'm trying to bring something new for most of you at least. I'm going to talk about freshwater lens behavior with climate change a little bit, but mostly also as about connection between land and sea through groundwater. Starting with the basics, just a little bit. So under many islands, we would expect a fresh groundwater lens, meaning that there's fresh water basically swimming on top of salt water. On the picture, it's the lighter blue fresh water with on top of the darker blue salt water. And that lens thickness, we call this the freshwater lens, and that's the lens thickness is defined by the groundwater hydraulic head. And basically, nearly 150 years or 100 years ago, they came up with the equation that the lens thickness, the maximum thickness, is about 40 times the hydraulic head. And in general, we can say that groundwater flows outward permanently around the island. The speed of flow, of course, is defined by the aquifer material and by the hydraulic gradient and other factors. And here you can already see that there can be different lithologies, different rocks. At the bottom, there would be limestone here, and at the top, there would be siliciclassic sediments. So that can be quite different. There's another situation that we have to think about, and you see that here at the bottom, which would be groundwater pumping in such a situation. So we are zooming into the edge of such a lens, and you see the freshwater table basically lowered by a pumping well. And that, of course, also allows the marine water to basically be sucked up, and then you would pump salt water at some point. So that can reverse also this flow pattern, because suddenly you have marine water flowing inward. We would call that saltwater intrusion. So these are basic principles that I'm going to talk about. First, I will show you a few examples of islands that we have been looking at and what we did there. And then I will go on to ecological effects, to societal aspects, and then to climate change. So a first small example of lens behavior that we've been looking at is Gili Air. Gili Air is a tiny Indonesian island. You can probably see it on the map. It's basically right next to Lombok, and the whole island is maybe a kilometer in diameter. So it's really small, but there's a lot of tourists coming there, so they have a lot of water issues. And we try to estimate how does the lens change, how does it look like, the freshwater lens, and what can we say about it? What can we say if it is sustainable or if it will probably shrink? So the first thing was really to try to map out the salinity of the groundwater. And here you can see the island, and then a blue shape in between, in the middle of it, and that would be fresh groundwater, basically. So it's groundwater with a salinity below 2.5. And we can see it's not under the whole island, but it's well in the center. And so then we used, and there was a master student who was there for several months and tried to get all kinds of data that he could get with the simple means we had. And we put that in a ModFlow model by another master student, which you see on the right side. So that would be a numerical groundwater model, also looking at density-dependent flow, which is very important here because the salt water is a little more dense than the groundwater. This is why the groundwater swims up. And you can already see here the shape of the lens, this lens-formed shape of blue, purplish, fresh groundwater, salinity of 0. And then below you see the fresh water, so that the salty water, brackish and salty. So that worked out quite nicely. And you see that the freshwater lens is about 20 meters deep, 20-something meters. And that's actually quite reasonable because the hydraulic head is maybe 1 meter high. So it's a very flat island. Just 1 meter of hydraulic head of groundwater elevation can produce 20 meters of lens. And then we modeled how it looks like if we add pumping wells to this groundwater lens. And there you can immediately see that the lens shrinks the whole volume, but also that those pumping wells, you can estimate where they are. They really suck up salt water very quickly and very strongly. And to us, that was quite impressive to model that and to see how strong the effect is. And we see that also on the island, of course, that some of the wells are saltier. But for the whole freshwater lens, we checked recharge, groundwater recharge, and we compared it against withdrawal and discharge. And it actually looked like that the usage, despite all the tourists, was not so problematic. But this is a very simple ModFlow model, and we just had very simple data. So it's really hard to say something. I think that's the main thing that we found on that island is, for us, it was hard to say something quantitatively, but it looked really interesting. It was a nice exercise. The second example is Gili Trawangan, which basically is right next to Gili Air. It's the island really next to it. Similar in size, just a few kilometers. And this is a story we're just developing, and something we're just working on. It's a master thesis that just actually finished 2 months ago. And you can see the island, and you can see all the touristy homestays and hotels and places where tourists stay. So the island, again, is fairly flat, but there's a mountain to the south. And we would expect either a similar setup, so fresh water in the middle, or actually historically there was no fresh water. But what we observed was, you see the island here, and this is an observation. This is not yet model research because the model actually doesn't look that much different. But you see some brackish water in the north, and then in the east and the southeast, you see those purple freshwater. And so we do have a freshwater lens. That to us was surprising, and or to the colleagues who were there a few years ago, and this is why we went there and had a little bit more of a look. But the cool thing there is, or I don't know if it's cool, that freshwater lens is not in the middle of the island, as you would expect if you would have rainfall or basically normal recharge or homogeneous recharge, but it's right under the village. So the freshwater, the salinities, again, they're taken from a lot of different dug wells, but the village, those hotels, often have sewage tanks. They have basically septic tanks, and those septic tanks are designed to leak. And so we hypothesize, and the models kind of show that this is the most likely variant, that the freshwater we see is freshwater from septic tanks. And I think that was, to us, very interesting to kind of note that we have not a managed aquifer recharge, but an unmanaged aquifer recharge on that island. Why is that relevant? Not only because it could be used for showering, or it is used on the island for showering, not for drinking, I think, but at least for showering. But also that we know from the literature that there is impacts of groundwater discharging groundwater to coastal ecosystems. And this is what I'm coming to right now. We had a look at two different places because we knew from the literature, as said, groundwater discharge is responsible or has been shown to be responsible for ecosystem effects. So we looked on the left side, that's Mauritius, and on the right side, on the left side, that's Tahiti in the Pacific. On the right side, that's Mauritius in the Indian Ocean. On the left side, we did a kind of a classical setup. We put up those gray panels over a submarine spring. So right in the middle of the picture, you see some blurry face. This is freshwater discharging into seawater. This is a submarine spring. And we had a look at how much algae growth do we have over 2 weeks. And after 2 weeks, we got those plates and checked how much was settled by algae. And we could see that the settled area went up to 20% right next to the spring, right in the middle of the picture here, while outside it was much lower. So we can say there's more algae growing close to the spring. This is, of course, a risk for eutrophication in situations where you don't want to have a lot of algae. One of those situations would be a coral reef. And that's what we see on the right side here. There we had there on Mauritius, we also know globally from fishermen, they say there's more fish close to submarine springs. And we were really intrigued by that and wanted to check that. And so we compared a spring influenced and spring sites on the left side here. You see those stars represent where we identified springs. And on the right side, here's a controlled site. There's no springs that we at least knew about. And then we took pictures, about 4,000 of them, every 10 minutes for about a week. And a master student that was pre-AI counted the fish on the pictures. And we could see that the sites with the springs have clearly more fish. The abundance of fish, the number of individuals was significantly higher at the spring sites and at the spring influence sites than at the control sites. Now, this is just comparing one site to another. There can be a million of reasons, but we found fairly consistent that there were more fish also at different locations at spring sites. So we clearly see some influence of submarine springs and submarine groundwater discharge on coastal marine ecosystems. I think it's important to keep that in mind when thinking terrestrial freshwater. There's another aspect that I'm honestly really fascinated with. That's the societal relevance of submarine springs. Again, this is an example from Indonesia, but we have collected in the paper that's cited down there, we've collected examples from all around the world where submarine springs and fresh groundwater seeping into the ocean is, for instance, considered holy. As here, there's a temple, it's called Tanah Lot. It's on the island of Bali. And there's a story that the Holy Spirit came and took a spring from land and put it into the ocean. So that temple is only accessible at low tide. And obviously, this is quite important for people there. I think it receives 2 million tourists and is relevant for the people who live there. And then there's places where people actually still use and drink the water, as down there. This is an example from Lombok, Indonesia, again, where we found wells in the ocean and people use that water. I think, to me, from a European perspective, where the water is actually not used at all, or the submarine groundwater discharge is not used at all, this was really fascinating to see how abundant these usage examples are around many island communities. And I think that's something that should be mentioned. And so if someone, that's also an invitation, if someone has a story to share about groundwater discharge or springs of any relevance, that would be really interesting for me also after the talk. And now these things, of course, also change. How would climate change impact coastal groundwater? And I'm not going to talk about changes of rainfall patterns or evapotranspiration or then also groundwater recharge. I'm going to talk about the most simple case, which is sea level change. Because here we have a situation where you have, again, the edge of a freshwater lens with fresh submarine groundwater discharge coming out. You have some forest situation or some trees close to the beach, and you have an irrigation well for agriculture. You see a little bit of drawdown, but there's no problem yet because there's no salt water that could be sucked in. But then, when the sea level rise increases and the sea level rises, the groundwater level also rises, and the salt water pushes landwards. So the boundary between fresh and salty groundwater is pushed landwards, and there's a saline wedge that goes below the freshwater lens. And this, of course, can be sucked up, and this could lead to salinization of the well. At the same time, also those forests, if they get too much salt water, of course, I mean, maybe not mangroves, but others, they could also run into problems. And the second situation I would like to talk about, similar setup, we have, again, the edge of the freshwater lens, but then there is some village structure here and a spring. Again, the sea level rises on the right side, and then also the groundwater level rises. If it does that, we can get localized flooding. We can get flooding on land. That's basically groundwater flooding, not seawater flooding, just because the groundwater table rose. If the groundwater table rises at the same time, septic tanks of that village could get into the groundwater, and that could lead to wastewater leakage. And that leaked wastewater can then be transported into the reef, which could degrade. So there's all kinds of connections in this groundwater, seawater systems that are probably going to change with sea level rise and also with other climatic changes, of course. I think it's a very dynamic system. It's really worth looking down to the groundwater also. And that already leads me to tips and best practices, kind of summary that I was supposed to say. I think maybe our practices are not best, but I think it's good practice to try to set up some kind of model of groundwater, and for that you need some groundwater data, but not too much. Of course, then the model is not going to be too accurate. It's always a trade-off, and the aquifer attributes are key to understanding and to quantifying with those models. And then I think it's important to keep in mind that discharging groundwater affects coastal ecosystems, and there is a land-ocean connection, and that should be kept in mind when you think freshwater resources. And then I would like to highlight that I'm actually really looking for stories on submarine groundwater discharge and submarine springs and their usage. So if you know anything and would like to share it, also afterwards, pay email or anything, it would be really interesting. And of course, if you're interested in those stories, I can share the paper too. And I'm looking for geological maps of islands because I'm currently trying to build up a a global model of island hydrogeology. And for that, I would need geological information. So if anyone has something to share there or wants to share it, it would be great to be able to get some of that. But in general, I'm really glad to answer questions right now, also later per email. And I'm also always open for collaboration because ZMT, Leibniz Center for Tropical Marine Research, we try to work together a lot with people in tropical communities and in projects that are relevant for people on the ground. So with that, I would like to close and hope I'm in time. Thanks a lot for your attention.
Thank you very much, Niels. Yes, you are right on time. It's perfect. And does anybody have a question for Niels in the audience? You can turn on your microphone and your camera and ask questions directly if you want. If you don't have any questions, I have a question. But all right, actually, I'm going to start with the questions then. Niels, thank you very much for your presentation. And I was wondering, what software do you actually use to create the models that you showed with the colors from the groundwater?
Mm-hmm. We have used FeeFlow, which is a commercial modeling software, but we have since transitioned to ModFlow, which is a free software for numerical modeling of groundwater.
Oh, great. Okay. I have another question if nobody has a question. I was wondering on an island, let's say, for example, on Gili Travangon, I don't know if I have the correct pronunciation, but do you know how many wells or how many boreholes are needed to create kind of a model that is starting to be accurate?
We have, there are quite a lot of duck wells that we used. This is not ideal, but it's okay-ish. The key data that we were usually missing are permeability information about the aquifer. That was always a problem, and I think that's usually for us the most difficult one to acquire. That leads to the most uncertainties, and also the depth of the aquifer. Like how deep do we expect it to go? That was also an information we didn't get, and then in that case we basically have to guess. And see how sensitive our models are to that information.
Okay, and did you actually have to create some new boreholes and wells, or did you actually get the local population to agree to help you and they were actually excited by your research?
Yes, I was not there personally, but I think from what the master student told me, they were excited. So they agreed to help us and let us basically monitor the water levels in their wells. That was what we did, and we did not create any own boreholes because we didn't have the means to do that. The project was just not big enough, so we had to rely on things that we immediately could take. But the master student, he was very enthusiastic. He was there for 6 months and really took time to talk to people. And also, at the end, we built up a small poster showing what we produced, basically.
Okay, well, this is great. Thanks. Chris, you were the first one to raise your hand. Please go ahead.
Yes. Hi, Niels. Thank you very much for the presentation. Very interesting. I was interested much in the fish, the spot where you took the fish. Yeah, you said eutrophication. It would be interesting to. It would be interesting, or have you ever gotten a result where we can find sort of like a threshold where it can say like, okay, this is eutrophication is good, but to what degree, like we understand that it'll yeah, the nutrients are good for fish, but to what degree is it a threshold that it becomes bad for the environment, Yeah,
Yes.
I wonder if you have that data already or something like.
I mean, that's a really important question because the groundwater discharging is often portrayed as a threat to a coastal ecosystem. But I think at the same time, it does sustain coastal ecosystems. So, because yeah, they do need some nutrients. The level of nutrients that you can tolerate really depends on the ecosystem that you're looking at. I'm not a coral reef biologist, but to my knowledge, they tolerate basically no nutrients at all, or as low as possible. They probably need something because they also want to live. But if you look at a muddy mangrove, for instance, you can have many more nutrients in those systems. So anyway, it's well below what we would consider drinking water thresholds. So yeah, I think generally fairly low. And I see Pearl nodding. She seems to know it maybe even better than I do. But I think it's, yeah.
No, I don't know better than you, but I do agree that I do think that the level would be lower than the drinking levels, because I mean, yeah. It's you're in salt water still. Juliana,
Yes.
you raise your hand. Do you want to say
Hi,
something?
everyone. Am I audible? Good
Yes, you
morning
are.
from
Yes.
Australia. Okay. So I'm Juliana doing my PhD in ocean engineering, but few years ago I did my master's in water engineering, and just recently I was working with UNICEF in Papua New Guinea, so I was also engaged with some groundwater projects. There were some occasions where we had groundwater in the coastal areas that had contamination, and I'm interested to ask Niels, if there were some information you guys also modeled contamination using ModFlow, because I believe the software also has a component or a model, a mod, I think a mod, I'm not too sure. I used that software ModFlow some years ago, so I also modeled some contamination in groundwater. So probably you can also put that in your models for modeling groundwater on the islands. So looking at the water quality is also a very important aspect for island communities. So I'm happy to collaborate. I also worked in water projects back in Papua New Guinea, but I'm currently doing my research in desalination. So I'm trying to embed those concepts in water engineering with desalination for island communities. So also, Niels, I shared the geology, the link there. So recently I did some geology studies for Papua New Guinea as well. And I'll be publishing a paper soon, but I think that link will be helpful for you to get some information. Thank you.
Thank you very much, Juliana. And actually, we did last year a capacity development workshop on ModFlow, and Chris was at the maneuver, and this is something we want to do again this year. So maybe I wrote down quality and ModFlow. Maybe this is something we can actually add into our capacity development that will be organized later this week with Chris. Niels, if you want to add something.
First, thanks a lot for the link and the hints. And yes, we've been looking into contaminant transport too. The issue there is always if you want to do it reactively, so if you want to allow the contaminant to be reduced by the environment, that we often don't have the numbers for that. We don't know how fast they would react. But if you look at conservative transport, that's something that's indeed fairly doable and already gives an idea because it tells you where the contaminant goes and where it probably will end up. And that's already interesting.
All right. I see the time is flying and so many good questions. So thank you all very much. And I'm going to give the floor straight away to Jackie Reed, that is our second speaker. So we still have some time for questions after. Jackie, the floor is yours.
Great, thanks, Pearl. I'll just share my screen. Just double checking you can see the presentation. Great. Thanks. Great. So yeah, thanks again for having me today. I'm going to talk about from flood models to meaningful warnings. So how flood modeling can support impact-based forecasting. I'd just like to acknowledge that this example is based on work we've done in the Raki catchment in Fiji. And so some of our colleagues are online who were part of this project and part of this work. So I'd like to acknowledge Vili Verivalu from Fiji Met Service and John Carrion from SPC. So yeah, we did this work together. So if you have any questions, there'll be 3 of us at the end to answer. So just to set the scene, currently in Fiji and around the Pacific, flood warnings are based on rainfall forecasts plus observation data. This infographic here just talks about the role of hydrological services. So basically using observation networks, looking at rainfall volumes and water levels in streams. That information is analysed, and in combination with the rainfall forecast, the hydrologists use their best judgment, plus on what's happening on the ground from situational reports to make the flood forecasts in Fiji. So currently, the rainfall forecasts look a little bit, I'm paraphrasing, but look a little bit like this, and describing recent rainfall, rainfall that's been heavy, and the river level being above flood alert threshold. So, for example, a flood warning continues to be in place for Raki town, low-lying and flash flood prone areas. So flood warning is in place for low-lying and flash flood prone areas. But from this information, it's hard to understand, guess what the extent of the flooding will be, what will be inundated, where will it flood, will the roads be closed, and what do I need to do? So in this village at the top of the screen here, what do they need to do? Do they need to evacuate? Do we need to do a full evacuation, get all our belongings out, or is it a case of just moving those belongings to a higher place in the house and just perhaps moving stock out of the way? And so what we have at the moment is looking at the rainfall forecast gives us, about a 6-hour window that there's a potential flood coming, and then there's about an hour to 2 hours between observation data upstream to downstream. So not much time, but I would say in Fiji we're very well warned that a flood is coming, but it's trying to understand the next step of what to do, understanding the magnitude, timing, and the frequency. So the aim, as I said, is to increase the understanding of the impacts to be able to provide actionable advice. So in addition to that forecast, adding this impact information. So at the top of the screen up here, so access road to Vatikatheva village is likely to be undated and dangerous to cross for a number of hours. So that gives the community up there an idea of whether they need to leave now if they need to get somewhere, or be prepared to stay put. Similarly, for this school in the middle of the catchment, perhaps it would give the students time to evacuate or leave school before they get stuck at school and aren't able to cross that river. And water is expected to inundate agricultural areas. So if farmers know that, they can make decisions on what to do. And water is likely to enter low-lying buildings, so that during this flood, it's likely that we'll get wet floors. And a key way to do that is to add an additional layer to the hydrologist toolbox through flood modelling. So looking at that observational data, but supplementing it with flood modelling to improve that flood forecasting and resulting in impact-based flood forecasting. And so with the short time today that we have, I'll briefly take you through the process of flood modelling that we undertook in the Raki catchment. Some of the areas of uncertainty and how we sought to reduce them. So basically, in hydrological modelling, we use a model to estimate volumes. So we break up the bigger catchment. This is the Raki catchment. We break it up into these smaller catchments, and we estimate the volume of water from rainfall. So if it rains on each of these catchments, how much water will infiltrate and how much water will end up in the river, the time it takes to get there, and so then eventually how it moves down the system. So by the time you get to the end of the system, what's the total volume running through the catchment at that time. And the key inputs we have are rainfall information, area, roughness, or which is proxy for land use, stream length, slope, and a range of parameters. I guess the crossover with this group is that GIS is an essential part of the toolkit. So it's used to determine the catchments, the area, the length, the slope, using elevation data, and then obviously using satellite-derived land cover and verifying the land use and therefore the roughness using satellite imagery. And the roughness is just a representation of, I guess, what's on the surface of the earth and how quickly the river will, how quickly the water will move over a surface. So a forested area, water will move slower getting through those trees than, say, a plain bare soil, for example, where water can rush over more quickly. And the other key inputs are hydrological observation data, including rainfall and stream flow. So basically, hydrological modelling simulates the relationship between rainfall and river flow. It uses historical events to understand catchment behaviour and predict the responses under different rainfall scenarios. So, having said that, the more historical events that we have to test it against, the more accurate we can get the model. So this is just an example of some of the data sources that we have in the Raki catchment. In an ideal world, we'd like to have 20 years of continuous instantaneous rainfall and stream flow to ensure that we cover a range of events. But what we're really looking for is this crossover, so you can test the events when there's water level, when we've got instantaneous water level at the same time as instantaneous rainfall. But often in data scarce regions, it's not possible. So we need to look at other data sources to supplement what we have. So this is just an example of what we had in the Raki catchment. You can see that we've got some water level data, so some pretty longish records, maybe 10 years around the catchment. Instantaneous rainfall, we've got some good coverage, but maybe 15 to 18 years. And then we also looked at other sources, so satellite data and daily rainfall. And you can see that we've got really good long records of daily rainfall throughout the catchment. So using that information, we kind of supplemented what we had to improve the data sets. So once we put all the information, calibration is the next step. And it's a critical step in the modelling process. So it involves adjusting modelling parameters so that the simulated river flows closely match the observed flows from past rainfall events. So that this can give us confidence that the future rainfall scenarios will produce realistic results. So these are just 3 examples from different points around the catchment. I think the black line is the observed flow, and basically what we're trying to do is get this blue line, this blue hydrograph, to match the black line. So this is flow on the left-hand axis versus time on the x-axis. And then once we have that, so once we run it in, we can run our different rainfall events. And once we have our flow, we can use rating curves to relate that flow to a water level. And a rating curve, I'm sure some of you are aware, but a rating curve or a stage discharge relationship, it describes the relationship between the river water level, which we have on the left, and the river flow or the discharge at a specific location. And so that's a lot of effort and a lot of work from hydrologists go into creating this or developing this relationship or determining this relationship. But effectively it allows continuous water level measurements, which is relatively straightforward, just measuring the level in rivers. It allows us to link that to flow. And to develop that, you've got to kind of do a lot of measurements under a range of conditions. So high water flows, medium water flows, and low water flows to get the full range of this curve, which can often be quite challenging. So yeah, as I said, in practice they're developed over time that tries to best represent how the river responds as levels rise and fall. And so with that combination of information, we can run a range of rainfall scenarios to try and understand what our water level will be. So this chart here, this is our design scenario. So basically, if you look on the top axis, this is the depth of rainfall. So if you have 60 millimeters of rainfall falling in 60 minutes, this is your resultant rainfall. And so we tested a number of scenarios. The purple and the reds at the top, they're the more intense rare events, and the yellows and greens are your more regular common events that produce lower water levels. And so with that information, you can then make that link between rainfall and water level. So if you get a rainfall forecast, it gives you, I guess it gives you more time to try and understand what the magnitude of an event will be. So if you get a rainfall forecast, say it's going to be 150 mils, you can kind of get a good understanding of what the resultant water level at your gauges will be. So once we have that information, the next step is to understand what the impact of that flooding is. So what is the predicted impact of that water level? And to do this, we use hydraulic modelling. So hydraulic modelling shows how water moves through rivers and across floodplains. It helps estimate water depth, flow speed, and where flooding is likely to occur. We used HECRAS for this, which is an open, it's a free software, not open source, it's a free software. And I did forget to mention for the hydrological modelling, we also used a HEC product, HEC HMS, which is also a free software, widely used free software. But for the hydraulic model, sorry, this is to say we go from rainfall to impact. For the hydraulic model, it uses flow as an input, so the outputs of our hydrological model, and elevation data. And elevation data, it really matters for modelling. I guess that's one of the key points to make. The level of detail in the elevation data has a big influence on the results that we get. So it really needs to match what we're trying to do. So if we just want a broad picture of how water moves in a steep or high level terrain, lower resolution data like SRTM, satellite derived 30-metre data might be fine. But if we're supporting disaster risk reduction in towns or villages, we need high resolution elevation data to properly capture the roads, the buildings, the drains, and how floodwaters will actually move. So you can see on this, this example here, we've got our Google satellite image on the left, our satellite derived DEM in the middle, and LiDAR. So we captured LiDAR for this project. And you can see on the right just the detail that's in that LiDAR. So I guess the big key things to note are the rivers that you can see running through it that aren't evident on the satellite derived DEM. And this is just an example of that. On the left is the SRTM, on the right is the LiDAR. If you draw a cross section through that, down the bottom you can see the red line. The red chart is the LiDAR derived DEM. The green chart is the SRTM, and you can see that the river channel doesn't actually isn't represented in that SRTM data. So for us, the level of detail we needed, it was really important to have that high resolution DEM. And hopefully this works. So for the modelling that we did, we gradually increased the river flow to see how each flow level shows up as a water level at our monitoring gauges. So this helps the forecasters clearly link the gauge levels that they're seeing in real time to how much flooding occurs on the ground and how far it spreads. Yep, that one. And then once we ran the model, we wanted to check how well the results matched what actually happens on the ground. But because there were no flood marks available from past events, we worked with the community and kind of drew on their deep knowledge and lived experience of flooding. So during community consultations, we had big maps out here, as you can see on the left, and people drew where they knew that flooding occurred, whether it came from resulted from the river or from rainfall events, where it always floods, what direction the floodwaters move, and had some good conversations around helping to validate those model outputs. I'll just briefly touch on uncertainty. In any model, there's always going to be ranges of uncertainty. And through this project, I guess we tried a number of things to reduce that uncertainty. So in terms of data quality, it was training, hydrological monitoring training, increasing the number of monitoring stations to increase that coverage of stream flow and rainfall distribution, collected LiDAR to supplement that elevation data, tried a few different methods of measuring velocity in the water to improve that rating curve, and then obviously the community consultations was a key part. And in the end, we developed these flood intelligence cards, and these flood intelligence cards, they look a bit crowded here, but they're specifically for the technical, the scientific officers at Fiji Met Service, and they're big A1 sheets maybe. They're not a flood forecasting tool, but they support improved flood forecasting. And so basically what it is you look at the rainfall depth. So as I said before, if you get 40 mils in 90 minutes, you know that you're expected to get 3.8 meters on your gauge in Raki Raki town. Because it's a 90-minute event, because it's a 40 mil, so we said 40 mils, it'll take about 80 minutes for the flood wave to get from upstream, so 0.1 to 0.3. And then at that 3.8 meters, we can expect widespread flooding of the market car park up to a depth of 30 centimeters, impacting buildings and flooding fields at the southern edge of town up to 60 centimeters. So that's the output. And in terms of tips of best practice, flood modelling improves impact-based flood forecasting. The quality of the data in equals the quality of the data out. You could do flood models everywhere, but the value of that flood model really is in using good quality data to inform more accurate outcomes. Small improvements can reduce uncertainty. LiDAR was important in this scenario, and community knowledge was also really critical, and community engagement. And that's it. So thank you.
Thank you, Jackie.
Yeah,
thank you for this great presentation. Oh, I see there are some raised hands. So let's go, Nicholas. Please go ahead.
Thanks, Jackie. Great presentation. Yeah, really good to see some of the outcomes of that work over the last few years. I was just curious as to, with the LiDAR for the Penang catchment, for example, did you have to do any cross sections to kind of verify depths in the catchment, and if so, how was? Because I wasn't sure when you flew the drones and did the LiDAR and everything with the consultant, was it dry season or wet season? Did the turbidity affect the results, and how were the results overall? Those are some of my questions.
Thanks, Nick. Yeah, so we flew the LiDAR in dry season, but there is still a little bit of water left. We didn't have, I guess, the capacity to go out and collect new cross sections, so we looked at the existing cross sections. So we had some, so Fiji Met obviously have some when they do their, when they install their stations, they do that. So we looked at that to kind of look at in the sections that we had it, how deep that water is and what the likely shape of it is. But we also took the view, I guess, that this is kind of informing the flood forecasting. I think if we were doing, we didn't do flood risk maps or flood hazard maps. And so I think if we were doing to that level of detail in the towns and villages, I think we would definitely supplement the LiDAR with cross sections, particularly near town where the water's a bit deeper.
Okay, thanks, Jackie. Great presentation.
Yeah, thanks, Jackie. Juliana?
Thanks, Jackie, for the presentation. It reminds me of my master's. So I did my master's using HECRAS, and HECRAS is a very interesting software. Just some things maybe just to add on to your study. So I used HECRAS back doing flood risk assessment, and some of the things that I understand from HECRAS, you can be able to model the flow, because that time I was using a 20-year data period rainfall data. And I was able to simulate the data and see how much time it takes to, for the flood to hit a particular city or town. So you can be able to see the timing if there's a flooding event that's going to happen. So I did like different written year periods, 5, 10, 20, 100. And if you simulate that in HECRAS, you can be able to see the timing, like how much time it will take for a 10-year written period flood so to hit that city. So you can be able to warn the guys downstream. So, and several things I also did use in HECRAS. I was able to model the sediment transport. So I also did some civil analysis on the riverbank. So I was able to identify what type of sediments were transported during that flood event. Another thing was water quality assessment as well. So there was some septic or sewage that were given off that were disposed into the rivers. So you can also use HECRAS to model that and to inform the municipal authorities as well. So there's just some things that I experienced using HECRAS, and I think it's really it's a very important tool that we can use in island communities too. So I'm also willing for collaboration, and I'm happy to work with any one of you who's maybe we can work together to publish some papers or so. But thank you.
Thank you, Juliana. I think you will be one of our speakers in one of the next webinars. I will get in touch with you because it seems you have many experience you want to share. Chris, I'm giving you the microphone. Go ahead. You raised your hand.
Sure. Thanks, Jack. That was very interesting. We're also working in Rakraki, but while you work on floods, we're on groundwater discharge throughout the catchment. Yeah, so I'd be interested if you would be willing to share your data with us, please. If I can reach out and thanks.
Yes, yep, absolutely. I think the LiDAR now belongs to the Fiji government, but yeah, definitely happy to talk
just your rainfall data and whatever you have already on hand. Yeah.
Sure. Thanks. We have a question in the chat from Salvin. So what is the ideal interval for taking cross sections in rivers? If you have an answer to this, or anybody else if you don't.
Yeah, I mean it's a tricky answer because there's no one answer. I guess it depends on what your modeling purposes are. So for example, if you were measuring stream bank erosion and you needed a lot of information on the shear stress or stream power, you'd need them closer together. you know, often you can measure it, but then you can do the interpolated sections in the model as well. But yeah, for flood modeling, I guess it also depends on the conditions of the river. So if you have a really heterogeneous river where there's a lot of different sections, you just need to be really conscious of making sure that you're representing it, the river effectively, really. So if you have big changes in the river, you want a cross section every time there's a change. But again, it also depends on what the resolution of your output is. So for this scenario, probably didn't need a high resolution of cross sections. We'd take anything that we could get. But again, if you were looking at a you know, really determining flood heights, you'd want them a bit closer together. So that's not really a helpful answer, but it's really dependent on the scenario.
Yeah, I can actually say, because I've been doing it in New Caledonia for many years. So in New Caledonia, the minimum we would go for would be 100 meters between the cross sections, because we needed to decide something so we can actually go with the surveyor to start getting the cross sections also on site. So yeah, 100 meter was really the minimum between two, and then getting higher 500 meters. But yeah, as you said, it really depends on the topology of the river, because if there's many twists and the banks are wider, or the major what's the name in English? The major riverbed is getting wider, then you do need to get this cross section. So yeah, there's not one answer that fits every river and every catchment. And I also wanted to add that in New Caledonia, we created a maximum flood records database, and I don't know if this is something that is actually existing in the other countries. And so I have two questions for you, Jackie, and for the audience. The first one is actually, do you know if you're in your countries, there's a maximum flood records database that is actually getting the inputs from the community, saying, yeah, for this cyclone, let's say, the water went that high in my house and stuff. So that's the first question. And the second questions I have for you, Jackie, after is, what explanation would you give to a decision maker so they can put some budget into the measuring networks and to get the data for water levels, for example? So first question, does anybody has a maximum flood records in their country? Do you know about that? Maybe SPC knows for everybody.
No, well, from our experience, I haven't come across it. I'm not sure if Billy wants to expand on that, but we haven't. I think there's a lot of information there, particularly in other agencies like NDM, like disaster management officers. But I don't think the next step of it has been undertaken to actually document and record that, from my understanding. Would that be right, Billy? Billy's microphone's not working. So, and then the second question of how would we communicate to decision makers the value of hydrological data? Well, Pearl, you've just really touched on so an initiative we've got at the moment in the Pacific is the development of a regional strategy for hydrological services, informed by national roadmaps or national strategies. And one of the key things that's very common amongst countries is that lack of understanding of the value of hydrological data, and something that we're working on in that advocacy space. But in terms of a pitch, I think it's I don't know how I'd pitch it. I mean, in an elevator pitch, it's that, I guess it's that data in, quality of the data in equals the quality of the data out. And often people are interested in this information during an event, during a flood or during a drought.
Crisis.
And it's hard to, I guess it's hard to convey that the value of hydrological data is in those long-term data sets and understand patterns and trends. And I guess it's trying to get the point across. So one thing we did look at doing is doing a hydraulic model with no data versus good data, and showing the difference between the outcomes. But that's a work in progress. But I think that could be something that would be beneficial.
Yeah, well, thank you. Okay, thank you. It's going to be the subject of one of our next webinars anyway, but as I have you here, this is something I wanted to have your point of view. Does anybody have a questions? We are kind of late on the schedule, so one more question, and if not, I will just finish the presentation so we can wrap up quickly. Thank you very much, Jackie, for the presentation.
Thank you.
All right, and so questions. Just quickly, there are some new articles, scientific articles around water and the Pacific Islands that have been published this year. So I can you can get the link with the QR code, and we will share the slides after the presentation anyway. But just so you know, some people are actually active writing stuff around water and groundwater for the Pacific. So it's very good. I'm very happy about that. Just so you know, this is the calendar for the next events we have. So next month, we are organizing a webinar the same way we did today around awareness on water management and what to say to the decision maker. So that's why I asked the question to you, Jackie. And then Digital Earth Pacific and the GIS tools for Earth observations. Right now, we are planning on a capacity development workshop around mode flow and coding with AI in July or August. The date will be shared with you when we have it. Just so you know, there's one groundwater workshop that is organized by the IAHS in Zimbabwe. But there's also the International Symposium on Water Resource Management that is actually organized in Canberra at the end of the year. I mean, not in September, actually. So this is an important information I wanted to give you, because Canberra is not far from the Pacific Islands. So it might be a good time for us Pacific Islanders to be represented in these events, and it might be the time for you to learn things actually and share with colleagues from the other countries. What's next up? Yeah, I created an interaction, but as we are late, I'm not going to do it. And so I just wanted to finish by thanking all of you for attending. And do you think we can actually turn the camera on so we can take a screenshot of all of you? Because I'm really amazed to see that we have so many people from everywhere. We have Germany, we have Suva, we have Kiribati that is in Samoa, actually. It's the first time we have somebody from Cambodia. So yeah, if you could please just turn on your camera for 1 minute so we can all see your great smiles. Yeah, Juliana. And then I'm just going to take a very quick screenshot, if it's okay with you, of course. So just give me your best smile. All right. Odd, will you be there? Nasir, Taufa, Chris, we want to see you, Chris. Come on, you gotta put up your face, please, Chris.
Sorry, I just got in.
All right, go for it. There you go. All right, everybody's in. I'm going to try to put everybody in the same model ensemble. Grande Galerie. Yes, there you are. No, that's not the way. All right, 1, 2. No, wait a minute. Sorry. How do I do this? No, it doesn't work. All right, 1, 2, 3, smile. They work. I'm gonna see. Paste. Yes, it worked. Perfect. All right. Thank you everyone for joining us today. And I hope to see you next month for the next webinar. And thank you again, Jackie. Thank you again, Niels, for being our very great speakers today and tonight for you, Niels. Merci beaucoup. Pula Vinaka.
Thank you, Paul.
Thank you. Thanks, Carl. Thanks, Nick. See ya.
See ya. Bye.
Thank you. Bye, everyone.